Good day, judges. Today, our team is presenting UrjaDrishti AI, a real time energy supply chain command center designed to optimize India's import resilience during maritime crisis. India's energy dependency is critical. We import 88% of our crude oil with up to 45% transiting the Strait of Hormuz. With a strategic petroleum reserve covering only 9.5 days of national consumption. Sudden choke point closures in the Gulf or Red Sea disrupt refiners, drive up landed costs, and threaten stockpile depletion. Traditional logistics tools operate in silos. They cannot parse real time threats or automatically trigger rerouting. UrjaDrishti AI bridges this gap. I am Varun. Joining me are Divakshi and Karthik. Now, Divakshi will explain supply chain digital twin.
Supply chain digital twin. To enable continuous what if scenario planning, we built a 3D geospatial digital twin of India's crude maritime trade routes using PIDEX. On the map, you can observe critical supplier nodes such as Basra in Iraq, Ras Tunara in Saudi Arabia, and Novorossiysk in Russia, linked by 3D flight arcs to major Indian refinery and SPR hubs like Jamnanagar, Mangaluru, and Vishakhapatnam. Under normal conditions, these routes are colored green, representing safe transmit. If we simulate a crisis, for instance, by adjusting our sliders to block the Strait of Hormuz or, or trigger Red Sea attacks, the PIDEC layer dynamically updates the arcs to red or orange delay colors. Below, our route registry table provides real-time route statuses showing whether shipping lanes are operational, delayed, or critical. This geospatial twin provides the foundation for our command inputs. Now Varun will continue with AI geopolitical risk intelligence.
Thank you, Divakshi, for your inputs. Now, we're going to observe the AI risk intelligent which is used in our website. This is basically the heart of our website. This monitors the risk driven by our geopolitical risk intelligent agent. Every time we click sync live intelligence, the agent scrapes live news headlines regarding maritime oil crisis using feed parser. It then dynamically resolves active Gemini endpoints from our Google Cloud catalog using the available GenAI list models, selecting the most stable active deployment. And in this case, we have used a Gemini Flash latest model. Gemini processes these headlines, performs sentiment analysis on shipping corridors, and extracts exact risk scores from 0 to 100 from the Strait of Hormuz and the Red Sea. To ensure the system remains 100% operational under restricted network environment or missing keys, we have implemented a rule based fallback keyword scanner. Furthermore, Gemini dynamically drafts a formal executive policy memo for the Ministry of Petroleum and Natural Gas. This memo updates automatically with the active risk scores and optimized allocations, proposing shipping guarantees, refinery adaptations, and conservation policies tailored to the crisis. Now, my friend Karthik will speak on math and optimization, which is used in the website.
In this section of procurement rerouting, we orchestrate our response using the adaptive procurement orchestrator. When geopolitical disruptions occur, we run a SciPy linear programming solver using the heist method to minimize India's total landed crude cost. Landed cost calculations include base price, freight, and risk penalties. Surcharges dynamically inflate Russian freight rates, while blockage parameters reduce the effective capacities of Gulf suppliers routing through Hormuz. In this normal 40% blockage scenario, the bar chart shows the model reallocating crude volumes, decreasing reliance on the Persian Gulf, and expanding intakes from Russian Urals and US Gulf Coast crudes. However, if we simulate an extreme crisis by raising the Strait of Hormuz blockage slider to 60%, the solver detects that total supplier capacity is less than India's 1000 MMT demand. Instead of crashing, the dashboard gracefully catches the infeasible state, flags a landed cost increase as and slash a shortage, displays the exact shortage in MMT, and prompts an active warning alert directing us to activate the strategic reserves. And next section comes to SPR analytics. When the optimizer detects a supply gap, we transition to strategic reserve optimization agent. We simulate India's 9.5-day SPR stockpile over a 30-day window under three scenarios. In scenario A, colored red, the unmanaged supply shock depletes our reserves completely by day 9, as no conservation is applied. In scenario B, colored orange, we applied the national fuel rationing slider input set here to 10% demand reduction. You can see the depletion curve flatten, delaying dry. In scenario C, colored blue, we model active SPR release. By configuring our SPR release slider set to 0.5 MMT per day, the daily supply gap is offset, protecting refineries and extending simulation enables government planners to mathematically balance rationing rates against drawdown schedules. Now, my friend Varun will continue.
Thank you, Karthik, for your inputs. Now, to summarize, UrjaDrishti AI integrates real-time feed monitors, generative AI reasoning, linear programming solvers, and time series inventory models into a unified, secure dashboard. The application is fully responsive and deployed live. Our code base is structured cleanly across our GitHub and documented well in our repository. UrjaDrishti AI empowers decision makers with the foresight to protect India's energy grid before disruptions strike. Thank you for your time.